section 6.1, graphs of sine and cosine functions. We'll start by getting the basic graph of f of x equals sine x. We'll start by taking angles that are multiples of pi over 4, plug them into f of x equals sine x to get the y component, and then plot the points and try to connect the dots. Starting off with x equals 0, sine 0 is 0. Sine of pi over 4 is root 2 over 2, which is approximately 0.7. Sine of pi over 2 is 1. Sine of 3 pi over 4 is also root 2 over 2, which is approximately 0.7 as well. Sine of pi is 0. Sine of 5 pi over 4 is negative root 2 over 2, which is approximately negative 0.7. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is negative root 2 over 2, and sine of 2 pi is 0. Now we'll just take each order pair, plot them on our xy plane. Now with our points plotted, we can see that our graph kind of makes a wave shape. It goes up from the 0, 0 to the pi over 2, 1, then it comes down to the pi 0, then goes down to the 3 pi over 2, negative 1, and then back up to 2 pi. But keep in mind that I can plug any x value into f of x equals sine x thanks to coterminal angles. So how does coterminal angles affect the graph of f of x equals sine x? Recall that to find the coterminal angles of the values we already have, we can do so by adding multiples of 2 pi or subtracting multiples of 2 pi. In orange, I've written down the coterminal angles that we would obtain by adding 2 pi to each value of x on our table. Each of these orange values of x, when we plug it into f of x, are going to still give us the same value. In effect, this is going to cause what we have in green to shift to the right 2 pi units. And by shifting every point to the right 2 pi units, you can see we get a duplicate of what we have in green. And we're not just limited to shifting our graph to the right 2 pi units, which would correspond to us finding coterminal angles by adding 2 pi. We can shift our graph to the left by 2 pi units by subtracting 2 pi from our x values that we already have. And by shifting our graph in green by 2 pi units to the left, we obtain the portion of the graph that we have in magenta. And if we shift that portion of the graph over another 2 pi units to the left, we obtain part of the graph that we have here in blue. And we can keep shifting to the left or to the right forever. And we'll keep getting this oscillation effect that looks like a wave. And there we have the graph of f of x equals sine x. It just looks like a wave that oscillates between negative 1 and 1. Now we're going to graph f of x equals cosine x, similar to how we graphed f of x equals sine x. We'll start by filling out the rest of this table, which uses the same x values that we used before. So one at a time, we'll just take each one and plug it into cosine x. Then when we plot our points and connect the dots, we get this portion of the cosine graph. Now, just like with sine, I can plug any number I want in for x. So how do I figure out the rest of the graph? Well, thanks to coterminal angles differing by integer multiples of 2 pi, all I have to do is shift the portion that I have now to the left or to the right by 2 pi units. And then I can continue to shift that portion over by 2 pi units to obtain more and more of the graph. Now, if we shift the portion that I have in green to the right 2 pi units, we obtain the part of the graph that I have in blue. And that portion in blue can be shifted to the right 2 pi units again, and we can keep shifting right 2 pi units indefinitely. We could also take our portion in green, shift it to the left 2 pi units, which is how we obtain the portion in orange. And we can take that portion in orange, shift it to the left 2 pi units to obtain the portion in pink. And then we can keep shifting indefinitely 2 pi units. Notice how our graph for f of x equals cosine x looks very similar to the graph of sine x. They both make waves that oscillate between negative 1 and 1. The only differences are where our maximum, minimums, and intercepts occur. The reason why these graphs are so similar is due to the cofunction identities. Recall that cosine of x equals sine pi over 2 minus x, which is equal to sine negative x plus pi over 2. So the graph of cosine of x is the same as the graph of sine of x, just shifted to the left pi over 2 units, and then reflected over the y-axis. What makes sine and cosine graphs so distinct from graphs we've seen in the past is the fact that a portion of its graph can be shifted left or right a certain number of units in order to obtain another portion of the same graph. This is a characteristic of special kind of functions that we call periodic functions. A function is called periodic with a period p if f of x equals f of x plus p for any x in the domain of f. As we stated before about why we were able to shift the portions of the graph over by pi or 2 pi units, due to the coterminal angles differing by 2 pi, then sine of x and cosine of x also have a period of 2 pi, which is why we were able to shift portions of the graph left or right by 2 pi units in order to obtain more of the graph. For any integer n, we have that sine of x equals sine of x plus 2 pi n, or cosine of x equals cosine of x plus 2 pi n. These properties are referred to as the periodic identities, which is what we've been using so far to evaluate sine or cosine at really big or really small angles. All we did was find a coterminal angle between 0 and 2 pi to the given angle, and then using that to evaluate. These identities basically say that what we were doing was valid work. Sine and cosine of x will equal sine or cosine of any coterminal angle to x. Transformations of f of x equals sine x or cosine x are referred to as sinusoidal functions. So sinusoidal functions are any functions in the form of y equals a sine of bx minus c plus d, or y equals a times cosine of b of x minus c plus d. Now, we could apply the transformations we learned in college algebra in order to graph these two functions. However, because of their properties, and due to the issue of them being periodic, we do want to look and use special properties of sinusoidal functions to help us obtain graphs. Now, throughout, we are going to assume that b is greater than or equal to 0. And thanks to even odd properties, this can always occur just by applying the appropriate property for the appropriate function. Now, our properties are as follows. The absolute value of A is referred to as the amplitude. The amplitude is the distance from rest, or what we're going to call the midline. The amplitude can be also found by using this little formula of 1/2 times the absolute value of the maximum value of our function minus the minimum value of our function. If we take a look at the figure on the right that I'm circling with yellow, notice how we have a variety of graphs of y equals sine x, 2 sine x, 3 sine x, and 4 sine x. Notice how the height of the wave is getting higher and higher. Now, the midline, in this case, is going to be our x-axis, and we'll talk more about how to find the midline later. But we can think about the midline as where the curve is always going to return to after we reach its maximum height or its minimum value. The next property is the period. The period of our sinusoidal function will be found by performing 2 pi over b. This comes from the fact that if we think about our transformations, b is a horizontal stretch or shrink. And when we stretch or shrink our sine or cosine graph, that is going to cause our period to get larger or smaller. If we look at the figure that I'm now circling in yellow, we can see the graph of f of x equals sine of 2x, f of x equals sine x, and f of x equals sine of x over 2. If b gets larger and larger, that's going to cause our period to shrink. So notice how the graph of sine of 2x has more oscillation within the same window compared to f of x equals sine x. And this is because the period is smaller. Meanwhile, if b gets smaller, like in the case of sine of x over 2, which would have a b of 1/2, that's going to cause the period to get larger. So it's going to take a longer time for sine of x over 2 to complete a period compared to f of x equals sine x, which we can see here in the teal graph. C over b is referred to as the phase or horizontal shift. Now, this is where it's a little different than transformations we've learned before. The negative c does cause the graph of sine x and cosine x to shift horizontally, but the phase shift isn't referring to how much we would move the sine x or cosine x graphs. The phase shift refers to how much we would shift y equals sine of bx or y equals a of cosine bx. So typically when we do the transformations, we would do the horizontal shift first, then we would apply the horizontal stretch or shrink. Here, we're thinking about how much we would have to shift our graph left and right after we've already applied the horizontal stretch or shrink. If the phase shift is positive, then we shift right, but if it's negative, we shift left. Make sure you are careful identifying the value of c. Because of the subtraction, c is the opposite sign that we'll see in the expression. D is going to be the vertical shift as we have seen in the past. Because d is the vertical shift, this is going to cause the midline to shift up d units. For our standard graph, y equals sine x, the midline is the horizontal line y equals 0. But since d is shifting our graph up or down d units, that's also going to cause this midline to shift. So if we look at the graph of y equals sine x plus 2, that's going to cause the entire graph to shift up 2 units. And that will cause our midline to also shift up to the line y equals 2. So d will also tell us that the midline will be at y equals d. Our strategy for graphing the sinusoidal functions is to utilize what we're going to call the key points. When we say key points, we are referring to the maximum points, the minimum points, and the points on the midline of our sinusoidal functions. The reason why we're focusing on these key points is these key points are always a quarter of the period apart. Within one period, there are going to be 5 key points. Now we're going to look over a strategy for graphing our sinusoidal functions by looking at the example of graphing y equals 1/2 sine of 4x. And our goal is just going to be to graph 2 periods of this equation. The first step is we want to start off by finding the phase shift, period, and amplitude of our function. The amplitude is the absolute value of a, and here in our equation, a is 1/2, and the absolute value of 1/2 is 1/2. Next is our period. Our period is 2 pi over b, b is 4, so our period is pi over 2. Next is our phase shift. Our phase shift is c over b. Since we're not adding or subtracting anything inside of the parentheses of our function, that means our c is 0, which means our phase shift is 0. Now that we finished step 1, step 2 is to take our period and divide by 4. This is because our key points are separated by a quarter of a period. Our period we found before was pi over 2, and if we divide that by 4, we get pi over 8. Now that we know how far apart our key points should be, we can now start finding our key points in step 3. Our first key point is going to occur at the value of our phase shift. Since our phase shift was 0, our first x-coordinate of our key point is going to be 0. And it does help to make a table to organize the key points. To find my next key point, I'm going to add the result from the previous step recursively to find the location of the other points. So from step 2, we got that our key points are pi over 8 units apart. So to get my next key point, we're going to add pi over 8. So my next key point occurs at pi over 8. And I'm going to keep adding pi over 8 until I have 5 x values. And as I add, I'm not going to bother reducing. This is because it's going to make it easier to plot later. And it's going to make it quicker to add as well. So my x value is 2 pi over 8, then 3 pi over 8, and 4 pi over 8. Now I know the location of each of my key points. Now I'm going to take each of these x values and plug it into my function in order to obtain their y values. Now, depending on what function we're working with, whether it be sine or cosine, there is a pattern that our y value should follow. If we're working with a variation of a sine function, our y value should follow the pattern d, a plus d, d, negative a plus d, and d. If we're working with a cosine variant, our pattern will be a plus d, d, negative a plus d, d, d plus a. You can either just plug in the values or remember the pattern. Whichever you find the easiest is up to you. The fastest would be to know the pattern. Our a is 1/2 and d is 0 since there's nothing added outside of our sine function. Since we're dealing with a variation of sine, according to our pattern, we should have 0 for the first y component, a plus d, which would be 1/2 plus 0, or 1/2, then d again, then negative a plus d, which would be negative 1/2 plus 0, or negative 1/2, then 0. And again, all of these values can be obtained by taking each x value and plugging it into our function. Now that we have our 5 key points, we can plot them on our coordinate plane. Now, after completing step 5 of plotting our points and connecting the dots, we've obtained 1 full period of our graph. However, the instructions did ask for 2 periods. So since we need more periods, we're going to shift each of our key points to the left or the right by the amount of the period, which here is pi over 2. So after shifting our graph that we had in red over to the right pi over 2 units, we obtain our second period here in green. If we had space available on the left, we could have also shifted our graph to the left pi over 2 units, but since I only have room on the right, we shifted to the right. But there are 2 periods of the graph of y equals 1/2 sine of 4x. Now we'll graph 2 periods of y equals 3 cosine of 2x minus pi over 4. Our first step is first we want to figure out the amplitude, the period, and the phase shift. The amplitude is the absolute value of a, and a will be 3 in this problem. So our amplitude would be the absolute value of 3, which is 3. Our period is 2 pi over b, and b is 2. So our period would be pi, and our phase shift is c divided by b. C is pi over 4, and our b is 2, which means our phase shift is pi over 8. Our next step is to take our period and divide by 4. Our period is pi, divide by 4, which we know is pi over 4. Nothing much we can do to simplify there. Now we can find where our key points are located. Our first key point is going to be located at the value of our phase shift, which is pi over 8. Now we're going to add our period over 4 to figure out our location of our other key point. To make the addition easier, let's obtain a common denominator between the pi over 8 and pi over 4. Now, we know the common denominator would be 8, and pi over 4 is equal to 2 pi over 8. And this is going to make the addition easier because we're not going to bother reducing our x values. We'll always have the same denominator for addition, and it'll make the addition a lot quicker. For example, pi over 8 plus 2 pi over 8 is 3 pi over 8. Add the 2 pi over 8 again, we get 5 pi over 8, then continue adding, we get 7 pi over 8, and then one more time, we get 9 pi over 8. Now to figure out our y values, we can obtain our y values by either taking our x values, plugging into our function, or we can use the pattern from the previous slide for cosine. And that pattern will be a plus d, d, negative a plus d, d, and a plus d. A we already know is 3, d is 0, since there's nothing added or subtracted outside of the cosine function. So our y values will be 3, 0, negative 3, 0, and 3. Now we can plot each point on our coordinate plane, and after plotting our points and connecting the dots appropriately, we have our first period of our equation. Now we're going to graph 2 periods of y equals negative 2 cosine of 1/2 x plus pi over 8 minus 1. Just like before, we'll find our amplitude, period, and phase shift. Our amplitude is the absolute value of a, which is negative 2. Absolute value of negative 2 is 2. So our amplitude will be 2. Our period is 2 pi divided by b, which is 1/2, which means our period will be 4 pi. Our phase shift is c over b, but be very careful with the value of c. Because of the plus 8, that means our c is negative pi over 8, and our b is still 1/2, which means our phase shift is negative pi over 4. We'll take our period, divide by 4, and we get pi, which means our key points are going to be 5 units apart. Since our phase shift is negative pi over 4, we're going to use that as the location of our first key point. Now to find our other key points, we do want to add pi. Well, since we're adding pi to something with a denominator of 4, we do want to get a common denominator. Fortunately for us, 4 pi over 4, which equals pi, already has a denominator of 4. So we're going to add 4 pi over 4 over and over again to figure out the location of the rest of our key point. So our key points are located at negative pi over 4, 3 pi over 4, 7 pi over 4, 11 pi over 4, and 15 pi over 4. To figure out the y values, we can take each x value, plug it into our function, or we can use the pattern of the key functions from the fact that we're using cosine. And our pattern for cosine is a plus d, d, negative a plus d, d, a plus d. In this variation, a is negative 2, d is negative 1. So using these values, we get negative 3, negative 1, 1, negative 1, and negative 3 as our y values. Now that we have our key points, we're going to plot them. And here we have our graph of our first period in green. Now to obtain our second period, we'll shift each point over to the right by our period, 4 pi. And there's our second period in red. Now we haven't quite talked too much about why we should pay attention to the amplitude. If we want to check to make sure our graph is correct, it helps to figure out where our midline is and make sure that matches up with our amplitude. Because d is negative 1, our midline is going to be the line y equals negative 1. Our amplitude represents the distance our wave is from our midpoint. Well, if we take a look and see how far our maximum or minimum points are from our midline, we can see that the maximum and minimum points are all 2 units away from the midline, which confirms that our amplitude is indeed 2, which matches the amplitude that our equation tells us it should be. Now we're going to graph two periods of y equals 1/2 sine of 4x minus pi plus 1. Just like before, we'll find the amplitude, period, and phase shift. The amplitude, which is the absolute value of a is 1/2. The absolute value of 1/2 is 1/2. Our period is 2 pi over b, which is 4, which means our period is pi over 2. Our phase shift is c, which is pi over d, which is 4. Now to figure out how far away our key points are, we'll divide our period by 4, and we get pi over 8. Since our phase shift is pi over 4, we'll start with pi over 4 as our first location of our key points. Since I know I have to add pi over 8, I do want to rewrite my phase shift or my period over 4 so they have a common denominator. Well, the least common denominator of 4 and 8 is 8, so pi over 8 already has the denominator of 8, but pi over 4 we can rewrite as 2 pi over 8. Now that our denominators are the same, the addition will be easier. And after adding, we get that our key points are located at 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, and 6 pi over 8. Now we can either plug in our x values into our equation, or we can use the pattern of sine for our key points. And the pattern for sine is d, a plus d, negative a plus d, and d. A is 1/2, d is 1, and our y values would be 1, 3/2, 1, 1/2, and 1. Now we can go ahead and plot these points, and there's our first period of our graph. Now we can shift each point over by pi over 2 units, and there is our second period in green. We can check just like before. Our midline would be the line y equals 1, and the height and bottom point of each wave we can see is half a unit away from our midline, which confirms that our amplitude is 1/2. Now we're going to try to write the equation that would represent the given graph. Now, in general, for sinusoidal functions, it doesn't matter if you use sine or cosine to write your equation. However, in our first example, we are going to use sine to express our function. In the next example, we'll use cosine. Make sure you read the instructions very carefully so that way you obtain the proper form. Thanks to cofunction identities, periodic properties, and even odd properties, there are infinitely many ways to write an equation for the same graph. Since we're using sine in this example, we know our equation is going to be in the form of y equals a sine of bx minus c plus d. Now we're going to figure out a, b, c, and d. Recall that the absolute value of a equals the amplitude. If you recall from our earlier slides, our amplitude is 1/2 our maximum value minus our minimum value. If we look at our graph very carefully, we can see that our maximum value is 5, our minimum value is -1, which means our absolute value of a equals 1/2 the absolute value of 5 minus -1, which equals 3. A could be positive or negative, but to make writing our equation easier, we are going to assume that a is positive. So we're going to make a equal positive 3. And now we have our first variable. But now how can we figure out b, c, or d? The next easy one to figure out is b. And keep in mind, it doesn't matter the order which you find the letters, so you don't have to find them in the same order I did. Whichever order you find easiest, feel free to find them that way. B is tied into the period of our wave. The easiest way to figure out our period is we're going to find the distance between our two consecutive maximum values. According to our graph, our maximum points occur at pi over 24 and 3 pi over 24. So how far apart are these 2 points? Well, we'll subtract the x components, and we get that they're pi over 2 units apart. Now we know we would calculate our period by using 2 pi over b. And from our graph, we know our period is pi over 2. Now we have an equation that we can use to solve for b. And when we solve this equation, we get that b equals 4. And now we've just obtained our second letter. The next letter we're going to focus on is d. We could find c now, but I just find d easier to find compared to c. D tells us where our midline will be. To help us find d, we're going to have to use the amplitude. Our amplitude measures the distance between the top of our wave to our midline. Since our amplitude is 3, from our maximum point, we're going to go down 3 units. And when we do, we land here at y equals 2. So our midline is at y equals 2, which tells us d equals 2. Now to figure out our value for c. C is related to our phase shift once when we know what b is, because recall our phase shift is c over b, and we know b equals 4. If we think about the pattern for our basic sine function, that would be d, a plus d, d, negative a, plus d, and d. Since we already know a and d, this pattern could be farther rewritten as 2, 5, 2, -1, 2. Now we'll highlight a portion of our graph where it starts with a y component of 2, then goes to y component of 5, then 2, -1, and 2. And there we have one period of our graph in green that follows our pattern of our sine function with our key points. Now you could highlight any portion of the graph that meets this pattern, but I specifically decided to start my pattern here because that start is closest to the y-axis. If we didn't have a phase shift, this pattern would start as a y-intercept. So in order to shift from the red dot, where the pattern would start without the phase shift, to the blue dot, which is where the pattern starts, that means the graph shifted left pi over 12 units. So our phase shift, since we moved left, would be negative pi over 12. Now we have our equation to solve for c, multiply both sides by 4, and we get c equals negative pi over 3. Now we figured out the last letter, which is c. Now we can write the equation of our graph. Y equals a, which is 3, sine, b, which we found to be 4, minus c. Well, because we're subtracting a negative, we'll switch that to plus, so plus pi over 3, and then plus d, which we found to be 2. And there's the equation of our function expressed as sine. Now we're going to use cosine to express the function that will produce the same graph that we saw in example 5. The only thing that's changing in our goal, instead of writing sine, we're just going to put cosine. So our equation, we want in the form of a cosine of b of x minus c plus d. If you recall our work from prior, our value of a, b, and d did not depend on whether we were working with sine or cosine. So we can use the same values of a, b, and d as we did before. So we can have a equal to 3, b equal to 4, and d equal to 2. What is going to be different this time is c. The reason why c is different because cosine has a different pattern for its key points than sine. Its pattern is a plus d, d, negative a plus d, d, a plus d. Since we already have a and d decided, then our pattern will be 5, 2, negative 1, 2, 5 for the y components of our key points. Just like before, I want to figure out one period of my graph that's going to follow this pattern, where it starts with a y component of 5 and then ends with another y component of 5. And I want to pick a starting point that is as close to possible to the y-axis as possible. That way I can use a smaller phase shift. And highlighted in blue would be that period that meets our pattern. If we did not have a phase shift, our pattern would start on the y-axis, which would be here. Our pattern, though, starts up here. How far would we have to move the red point to get to the orange point? That would be pi over 24 units. So our phase shift, which we calculate from c over b, is equal to positive pi over 24. And it's positive because we would have shifted to the right. We've already determined that b was 4, so c over 4 equals pi over 24, which means c equals pi over 6. Now that we figured out the last letter, we now can form the equation of our function in terms of cosine, and we get that our graph can also be produced by the equation y equals 3 cosine of 4x minus pi over 6 plus 2.